All right, so we've been talking a considerable length about kind of the logistic regression model. We said it's very powerful, but it's restricted. It's restricted in the sense that our y variable, right, for normal, ordinary logistic regression could only take two values, some type of yes, some type of no, some success, some failure. We said it would be nice to have some way to extend that model, and we said there's two possible ways of extending it, depending upon whether your y variable, so now we're considering the situation where the y variable has more than two outcomes, and we want to consider the situation where the y variable that now takes more than two outcomes is either ordinal, and that's handled or modeled by the proportional odds model, which we talked about last week, or the situation where it's nominal, where the categories of our y variable do not have any type of inherent ordering. That's what we're going to talk about this week. And this type of modeling is referred to as the generalized Logit model, right? So it's the Logit model. That's the model that we were using for a y variable that took two outcomes, and now we're generalizing it to more than two unordered outcomes. So examples might be we want to model someone's political affiliation, and instead of just the usual sort of two-party structure, we want to allow a third option for someone who doesn't really identify with either Republican or Democrat. Maybe we want to model a dietary preference. So maybe you prefer to eat fish. Maybe you prefer to eat invertebrate. What's invertebrate? Invertebrate is like snakes, isn't it? Things without spines, without backbones. It's a weird thing to have a dietary preference for. Maybe it's not students. Maybe it's bears, right? So maybe you're modeling a bear's dietary preference as fish, invertebrate, or others. So just a couple examples. We'll see one or two more as we move through this lecture. It can also be used for an ordinal variable y. So we can also use this model when y has ordered categories in situations where the proportional odds assumption has been refuted, where we did the proportional odds test and we rejected that test. So it works very similar, as we mentioned last week. If we have a y variable that has k outcomes, we need to build k minus 1 equations. The right-hand side of these equations are going to look very, very, very familiar to us. They're going to be, right, linear combinations of explanatory variables. So, right, very familiar to what we've done earlier in this class. Also, of course, familiar in terms of what we've done in our 512 class. So how does this differ from proportional odds modeling? It differs from proportional odds modeling in terms of what's on the left-hand side of our equations. So we structure the left-hand side differently, right? We can't do something like before. It was what? It was, right, the left-hand side for like equation k was like the probability y is less than or equal to outcome k over the probability that y is greater than outcome k, right? This idea of less than or equal to doesn't make sense if we don't have ordered categories. So we have to, by necessity, define that outcome different. And so I used that Logit term. I took it from our textbook, but that Logit term is a little bit of a misnomer because the Logit is technically defined as the log of that outcome over 1 minus that outcome. And that is not what's being done here. We're going to define the Logit, or we're going to define the left-hand side for some outcome k, for some outcome lowercase k, as the probability of that outcome k over the probability of some reference outcome. So we have to first pick a reference outcome it's a little bit like creating our dummy variables, isn't it? So if we had, like in 512, if we had a categorical explanatory variable with k outcomes, we picked a reference category and then made k minus 1 dummy variables for all the other categories. Kind of same idea here. Instead of these dummy variables, we're building equations. And we define each equation as the log of pi sub k over pi sub r, where r is our reference category. So note, this is not some probability over 1 minus that probability. And so in that sense, it's technically not how we defined the logit function earlier. Instead, it's the log of some probability over some other probability. Now, of course, right, if we only have 2 outcomes, this does in fact simplify to what we had before, right? If there's only 2 outcomes, then we have some probability. The other probability by default's our reference category. Now it does simplify into, right, the log of some probability over 1 minus that probability. But in the more general sense, with more than 2 categories, it is no longer, right, a probability over 1 minus that probability. And so, as I said, our logit model now becomes, right, how we define that left-hand side equal to, right, this linear combination of explanatory variables. This is different than last week's proportional odds model. It's different because the slopes are different for every one of our k minus 1 equations, which means that there's a lot of parameters that SAS has to fit now. So let's do an example. Real life example, based off a pedagogical study. Educational researchers wanted to compare 3 different approaches to mathematical instruction that were delivered to 3rd graders. The first approach was this kind of self-guided instruction where the students worked on computers, and the computers kind of guided the students through these kind of discovery exercises. The second approach was where students worked in groups of size 4 in this kind of collaborative approach. They all kind of worked collaboratively. Sort of teaching one another these different mathematical techniques. And the third was like a more traditional class, right? Maybe 15, 20 students, a teacher, and the teacher's lecturing, and the students are listening. All right, so kind of 1 and 2 are maybe some more kind of modern day novel approaches. Number 3 is like a little bit more old school, a little bit more OG. And so the students were exposed to all 3 modes of instructions, and then at the end of the day we're asked to pick the one they prefer, the one that they liked most. Now these students were selected from 3 different schools, so we have school 1, school 2, school 3, and they were also in one of 2 programs. So the students just were kind of in like a regular schooling program, right? 9 to 5ers, or I guess probably more realistic, or maybe 9 to 3 or 7 to 3 or something like that. But there were also some students that were enrolled in this regular schooling and then had a supplemental after-school program, this kind of optional after-school program that they could also be enrolled in. So it's really kind of, some of them were in this after-school program, some of them were not. Some of them had this sort of supplemental education, and some of them didn't. So the researchers had three main questions. The first main question was, is learning preference affected by type of program? So, right, some students were in this after-school program, some weren't. So we might consider these 2 different subgroups of students. Do these subgroups of students differ in terms of how they prefer to learn math? Does learning preference depend, or is it affected by the school, right? We had these 3 different schools, these 3 different elementary schools. And then the third question to me is maybe the more interesting of the 3. is the relationship between program and learning style, does that relationship differ between the different schools? So let's stop for a second and think about how. How would you answer each of these three questions? In our statistics program, we don't always actually kind of put the questions so straightforward. But of course, as a practitioner working with a non-statistician, this is the way questions are going to be posed to us. So we're used to, like, here's some data, and here's like our proc, and here's how we go ahead and here's how we pull the pieces of our output to answer like these questions that we have determined ahead of time are relevant. This is a little different. Someone is asking us questions, and we need to think about, okay, how am I going to write my code to generate these answers? And then how, once I've run my code and I have output, which pieces of output are the relevant pieces to answering these questions? So how are we going to answer these questions? And I think 1 and 2 are straightforward, but what about 3? How would you answer question 3? Think about that. How do you determine whether or not the relationship between program and learning style differs depending on which school you're at? Answer forthcoming. Yeah, so 1 and 2 are fairly basic. We're just going to look at the significance test for those variables. But what about question 3? Exactly. That question is essentially asking, is there interaction between the program variable and the school variable? Anytime you're looking at, right, whether the relationship between, say, school and learning preference depends, that is setting up the possibility of interaction. So we know we want to test the significance of a school variable and a program variable, and of course the interaction of those variables. So, right, these are categorical variables, so that means that we need to set up dummy variables. We can ask SAS to do that for us, but we still need to sort of be a little bit cognizant, a little bit purposeful about how we want to define those. So I'm personally more proficient, more comfortable with reference parameterization, so that's what I'm going to go forward with. Right, you as a student might want to practice with effect parameterization. This data set that we're using could be accessed from a previous lab. The lab, I believe, we looked at stratified S by R tables, so you can pull the data set up from that lab and kind of play around with it yourself. So let's go ahead and make school 3 our reference category. And let's go ahead and make just regular schooling our reference program type. So let's go ahead and write out our equations. And we'll make class instructions. So remember, in terms of our y variable is what? Our y variable is instructional preference. So in terms of our y variable, we have 3 outcomes. You could prefer self-instruction, team instruction, or class instruction. So it makes sense. Again, it's somewhat arbitrary, but class instruction is like sort of like the traditional approach, kind of the status quo. So it might make sense to make that our reference category and sort of see how these newer techniques are received relative to the more tried and true technique. So we're going to go ahead. We have to pick a reference category for our y variable. Let's go ahead and make class our reference variable. Okay, so here they are. Nothing too crazy, right? So 3 categories for y means 2 equations need to be fit. The left-hand side is log. So we said class is going to be our reference category. So that means we have 2 categories left over. So we need to look at the log of pi self, the probability of preferring self instruction over the probability of preferring class instruction. The other equation is log of pi team over pi class. And then like this, right, 2 equations, of course, right? There's a lot of subscripts. So if I look at that top equation, alpha 1, beta 1, 1 means the first variable, first equation, and then beta 2, 1 means second variable, first equation. Beta 3, 1 means third variable, first equation, and so on. There's a total of 5 variables, right? Because of, so in terms of like aggregate variables, there's 3. There's the school variable, the program variable, and our interaction of the 2. But remember, school has to be sort of, since it's a categorical variable with 3 categories, we need 2 variables to define it. So we need to consider the interaction between program and school. There's actually 2 such interactions, x1, x3, and x2 and x3. Now, why don't we do the interaction between x1 and x2? Maybe pause this video and think about it for a little bit. Yeah, exactly. We never do interactions between dummy variables that are components of one larger categorical variable, right? Because think about it, x1 and x2, like school 1 and school 2. That interaction term is going to always be 0, agreed? Because why? You can't be in school 1 and school 2. So one of those has to be 0. Maybe both of them will be 0 if you're in school 3. And so, right, that variable is not really a variable. It's like imaginary and not in the square root of -1 kind of way. So 2 equations, hopefully what you expected them to be. 3 variables, program and school and their interaction, but that essentially breaks down into 5 variables that need to go into our model. And of course, a y variable with 3 unordered categories means we have to fit 2 equations. So how do we fit these 2 models? How do we fit these equations? Well, we could do it in SAS. All we need to do is use the link equals G-Logit statement in the model statement of proc logistic. So G-Logit as in generalized logit. So there's our code, still using proc logistic. Man, you get a lot of mileage out of this proc. We need to use that freak statement because apparently this data was aggregated. We set up our class variables with the param statement. There's our model statement. Notice I put the interaction term in there just like I did from 512 using the asterisk symbol. And link equals G-Logit. Do the aggregate scale equals none to get my goodness of fit tests. Now, a little note on the code. If you want to change or explicitly pick your reference category for y, you can replace style, that's the y variable, with the notation style parentheses ref equals self in the model statement. So that allows us to explicitly pick which category we want to be our reference category instead of falling back on SAS's defaults. So here's our output. Notice on the very, very top it says model generalized logit. So that's what we want it to be doing. It gives us that response profile, right? It says it looks like most people picked class, 174 students, like, felt comfortable with the traditional way of doing things. Maybe that's why it's the traditional way of doing things. Although a sizable number, right? 85 did like team and 79 did like self instruction. So, certainly there was decent sized numbers in the other categories as well. Now, most importantly is that line where it says Logit's modeled use style equals class as the reference category. Always check that SAS is in fact using the reference category that you think or expect it to. Now, in terms of the class statement, SAS has to create these dummy variables. It shows us how it creates those dummy variables in the class level information. So here we can see it defines them just like we wanted them to. Right, when we're looking at schools, the columns are the variables. So 2 columns means 2 school variables. The first column is our x1. It's defined as 1 if we're in school 1, 0 otherwise. That second column corresponds to school 2. It's 1 if you're in school 2, 0 otherwise. Huh! That's unusual. What the cutta? Why do you think that SAS fails to provide us a goodness of fit test, or, right, looking at those like 0 degrees of freedom, why do you think the goodness of fit test is failing? Maybe pause this video, think about it. When you unpause it, I can go ahead and tell us the answer. Exactly. Remember, we said that like a lot of goodness of fit tests, and certainly the Stevens and Pearson goodness of fit tests, are comparing our model of interest to this higher level. What do we call it? We call it a saturated model, where the saturated model is kind of generating these sort of perfect predictions. Now, when we include all possible interaction terms, which is what we're doing now, for a model that has only categorical explanatory variables, that is essentially the saturated model. So in this case, we're fitting the saturated model. And so comparing it to the saturated model, which is what a goodness of fit test does, is comparing it to itself. And of course, there's nothing to be done statistically. And so that's why we see we see these goodness of fit tests failing. We can't really do a goodness of fit test. It doesn't really make sense in this context, because we're kind of trying to fit the largest possible model. Now notice we see our global tests. They're all highly significant, indicating that something's going on. We should dig deeper. We go ahead and dig deeper by looking at the type 3 analysis of effects. And what the cutta? I thought our very significant global tests indicate at least one of our variables is significant, but none of our variables are significant? That's weird. Oh, of course, because these are type 3. That's why. These are type 3 p-values. So they're not saying that those variables are completely useless in our model. Those variables are saying, right, for example, the school one does not add anything above and beyond program and the interaction between school and program. That's what's being said. And so what would we do? What is that telling us? Well, the typical backwards approach is to look at the variable that has the largest p-value. In this case, it's the interaction term, which has a p-value of 0.78. Remember that number, 0.78, the p-value of our interaction term. We're going to see it again down the road. So if we were to remove the variable that has the largest p-value, that would be our interaction term. Now, I would still, if that interaction term was non-significant but didn't have the highest p-value, I would probably still remove it first. as kind of like the variable with like the highest level of complexity, right? I always want the simplest, most parsimonious model. We talked about that in 512. So if it's telling me an interaction is not adding anything above and beyond those base terms, those main effects, I would actually remove the interaction first. And so we'll do that in a few slides. Right below are all like the estimated coefficients for our model equations. Again, I'm not even going to bother looking at those or talking about those because we've already seen and made the conclusion that we need to remove that interaction term. Yeah, I mean more parameter estimates. So verify SAS was using the correct reference categories. Check, we did that. We talked about why the goodness of fit test didn't work. We talked about how all three global tests, like almost always, agree, and they agree in terms of being significant. We saw none of the individual variables were significant, which seemed to contradict the previous slide at first, but then when we realized they're type 3 tests, we realized that they weren't necessarily contradicting it. And ultimately, we concluded what's being told to us is we should remove that interaction term. Now, going back to how the non-statistician, the educational researcher, posed the problem to us, does the relationship between learning preference and program differ by school? And the answer is no, it does not differ. That's essentially what the non-significant interaction is telling us, right? The fact that the interaction is non-significant answers that third question posed to us by the researcher. Now, we could remove that from our model, rerun the model, and answer questions 1 and 2. So proclogistic, same code, just removed the interaction term. Again, check to make sure that we didn't screw something up, that we still are using the reference category that we intend to. We are. It's that the class reference category. There's our goodness of fit tests. Now they're working because we're no longer fitting the saturated model. And so what is SAS doing? SAS is comparing this model, our model without an interaction term, to a model that has an interaction term, the saturated model, and lo and behold, look at what's the p-value of that test. It's very, very close to the p-value of the interaction term, right? Because essentially this goodness of fit test is testing, do we need an interaction term? It's doing it in a slightly different way computationally than was done in the previous output, but it's not surprising that that p-value is very, very, very close to 0.78. Well, it is 0.78. The other one was like 0.7827. So they're very, very close because they're essentially testing the same thing. All of those tests are testing whether or not an interaction term is improving our model. Now, our global tests all agree. All are highly significant, telling us at least one of our variables is useful in our model. We look at the actual aggregate variables. Both of them are significant. Learning preferences differ by school. They also differ by program. And there's our model equation down below. We could, of course, untangle that model equation to get things like odds ratios. And also, we could use the output statement to get things like predicted probability. So we could ultimately unravel this and see, right, for the schools, what are the different preferences for school 1, right? What percentage prefer class instruction? For school 2, what percentage prefer, for school 1 and program 2, what percentage prefer, say, class instruction. We could unravel all those different probabilities. All right, so more of that program. I'll actually write the model equations out, I think, in an upcoming slide. Notice here I also generated odds ratios. So right there's all the different odds ratios. I'll talk about how to get those and how to interpret those in just a second. I think the two that I focus on are the school 1 versus 3 for self-preference style, and school 1 versus 3 for team. I can't scroll back, but if you go back to the output, you'll see what? You'll see that we have essentially, what do we have? We have 2 different y-intercepts, because remember, we're fitting 2 equations, this self equation and this team equation. So we have 2 different y-intercepts. There's 3 variables and 2 equations, so we have 6 slopes that need to be estimated, right? Because the slopes for all 3 variables, school 1 and school 2, as well as learning, or as well as program, are different depending on which equation or which learning style we're comparing to classroom learning style. And so there's also different odds ratios. So we have an odds ratio. There's sort of 2 odds ratios comparing school 1 to school 3. One of those compares self to class. The other one compares team to class. And we have the point estimates for both of those, 0.269 and 0.519. We'll talk about those in just a second. So again, verify SAS is using the correct reference categories. The goodness of fit tests have high p-values indicating an adequate fit to our data. All 3 global tests still significant. School and program are significant. Both variables are useful to our model. Here's our model equations. I put that little hat over the left-hand side to indicate these are fitted equations. These are estimates of the true theoretical equations. So go back to the output and verify that you can see where all these numbers come from. I would certainly consider it fair game on an exam to give you output like before and ask you to write these equations like I've written them here. And of course, again, a thorough answer would define x1, x2, and x3. We've already done that on a previous slide. And so the last thing to discuss is our odds ratios. So each of them, remember, was comparing school 1 to school 3. Both of them was comparing school 1 to school 3, but one was comparing self to class. That was the first one. And the second one, the 519, was comparing team to class. So what that's basically saying is, right, this percentage of students who prefer self-instruction relative to class instruction for school 1 is 0.269 times that of school 3. I'm avoiding the use of the word odds because odds are technically defined as the probability of some event over 1 minus that probability, and that's not what we're modeling here. We're actually modeling, right, the percentage of self over the percentage of class. And then we have these two ratios, one for school 1, one for school 3, that are being compared. And then the same idea, the estimated percentage of students who prefer team instruction relative to class for school 1 is 0.6556 times that of school 3. So, I mean, there's a lot going on there, right? Because we are comparing school 1 and 3. We're also comparing self to class, and then we also have to compare team to class. It is a lot to have to digest. This is, right, your most complicated model, this generalized Logit. And so complicated models are hard to interpret. So if you're having a hard time wrapping your head around it, it's understandable. What's really being said? Well, what that first bullet point is really saying is that in terms of school one, less students, a lower proportion of students prefer that self-instruction. The proportion of students in student one that prefer self is smaller than that of school three. Also, the proportion of students in school one that prefer team is smaller in school one. And so consequently, that means the number of students that prefer class instruction is higher in school one. So school one relative to school three liked class instruction more and self, so it's kind of the traditional way of approaching it more, and some of these newer novel ways, self-instruction and team instruction less. So I don't know why. Maybe school one just has like a better teacher. So maybe the problem with a lecture-based style of instruction is it's highly dependent upon a teacher. And if you have a good teacher, it's going to be really effective and people are going to like it. But if you have maybe a less dynamic teacher, it's going to fall flat and not be effective. And so maybe that's what we're observing. Maybe school one has this really phenomenal hits it out of the park teacher. Maybe someone like maybe the great Professor Gallup. Maybe moonlights at school one as a third grade math instructor. You know, maybe it's not so much that they like that more. Maybe they like the self-instruction less because it's based off computers and they just have an older computers. They have slower internet. I mean, you know, there could be a number of reasons. That's something we'd have to look into. But right, the idea is like, how do we go from these numbers to like a big picture statement? Like, okay, school one seems to like self-instruction, team instruction less than school three, and also seems to like traditional instruction more. We're always striving. I don't always emphasize this. I sometimes really emphasize all these these mathematical kind of nuts and bolts interpretations. It's sometimes nice, and I'm going to try to do that more in this lecture and maybe the next couple lectures, to kind of just emphasize like a big picture kind of broad statement in terms of interpreting our data set. That might be something that a non-statistician might appreciate. Of course, the follow-up question might be, how did SAS get the odds ratios? How did SAS get the 2.69? How did SAS get the 0.5199? Well, they did it just like before. So you can get those things just like before by exponentiating parameter estimates. So if you go back to your model equation and you exponentiate the negative 1.3147, so that's that was the school one variable for the self equation, for the equation comparing self to class. Exponentiate that, and lo and behold, there's the 0.269. Go to the second equation, that's the one comparing team to class, and exponentiate its negative 0.6556, and that's where you get the 0.519. So that wraps up our discussion of logistic regression. We've moved from binary logistic regression to to generalized, right? To the situations where you have more than two outcomes. We looked at it for both a y variable that's ordinal and one that's nominal. Now we're going to wrap this class up by looking at two different approaches that are just kind of different topics than this. So just a couple loose ends to wrap this class up with.